So main school is starting from next week, from Monday. But this week, basically, I, Abhishek, who is one of the organizers, and then there's another lecturer, Abhishek, this Anupam Kundu. So we are going to cover some of the basic things which you might need for the future lectures, basically, from the next week. So I'm going to talk about stochastic processes, and Abhishek is going to teach random walk. And then this Anupam is going to teach basically some basics of thermodynamics and statistical physics, basically. Yeah. And so I request all of you to be present in all the lectures. Okay, I mean, attendance of this school is mandatory. It's not like you don't choose that. Okay, this lecture is I'm not finding very good, so okay, I just skip this lecture. So that's not allowed. So in the sense, let's say there are more than, I think, 250 applications, and from which we selected about 100 because of the space constraint. And so when we selected 100, other 150 we have left out, right? So if you don't attend these lectures, then those seats could have been filled by somebody else, right? So for this 2.5 weeks, even if you find some lectures difficult, okay, you are not understanding, so you can ask the lecturers, I want it to be more interactive, yeah? But please attend all the lectures, okay? And you have anything to else? Okay. So you have already seen that, okay, schedule for the lunch and dinner, and so all the foods will be provided here. And people who are staying in the Jalahalli guest house, okay, after dinner, there will be a shuttle. And then again in the morning, I think it's 7:30 today. What time is it? And what time did you reach here? 8. Is it too early or it is okay? It's fine, right? Huh? Okay, yeah. Yeah. Also use the microphone if you have any questions to ask, basically. Yeah. So, okay, so you can hear everybody? Yeah. So what I'm going to cover is, so it's a introduction to stochastic processes, but mostly I'll be focusing on something called Brownian motion, right? So most of you have probably heard about it, right? What is a Brownian motion? So imagine that you have a beaker and you put a micron size particle there, okay? You can take a polystyrene grain or a cholesterol bead, okay? A polystyrene bead, okay? So what happens is that, okay, so there are water molecules everywhere, right? And they hit the particle from each direction, right? There are continuous heating going on, right? So therefore, there is a force subjected by the bath, right? And you know that if you have a particle under some force, we know that it follows Newton's law, okay? So what are the forces this particle experiences? So one is, of course, if there is some external force, okay? So let's just call it f of x. So let's, for a time being, let's assume that it's time independent. So f of x, okay? So this is basically, imagine that if it is a charged particle, you are putting an electric field, that's an external field, right? Or it's pulled by the gravity, or you are putting in some confining potential. These are external forces, right? But there are also forces exerted by the bath, right? So what are these forces? So one force is, of course, if you take a, let's say, particle and if you drag it through the water, right? So there is a force by the medium, right? So what is that force? So this is a viscous drag. So this is minus gamma times the velocity of the particle, okay, and gamma is the viscous coefficient. So, if it is a spherical particle, so then gamma will be 6 pi eta b, right. But on the other hand, there is also a random component to this force, right, because all these water molecules are hitting from each side. Okay. So, I will just describe this force by some random number, okay. So, which property I do not know yet, and I am going to put something, let us just put it, let us call it A, 2A times eta of t. Okay. So, this is a random variable and there is some strength which I am going to determine. Okay. So, for the time being, so let us put Fx is equal to 0. Okay. So, then I know how to solve this equation, right. It is a linear first order differential equation, but okay, before putting this to 0, so let me just rewrite this equation slightly different way. Yeah, let us just put F equal to 0. Okay. So, I have an equation which is dV dt is equal to minus gamma by mv plus m eta t. So, this is the equation I have, right. So, I know what is the solution. So, V of t is V of 0 e to the power minus gamma by mt plus square root of 2d by m 0 to t e to the power minus gamma by m t minus t prime eta of t prime dt prime, right. For any function eta of t, I have this solution. Okay. Okay. So, now I am going to assume some properties of this random variable, random function. Okay. So, I am going to assume that it is symmetric, right. So, I am writing down in one dimension, you can generalize to any higher dimension. So, symmetric in the sense that the average of eta is 0, right. So, distribution is symmetric, so average is 0, right, because there is no reason that okay you have it is a homogeneous medium, right. These are water molecules are hitting from all directions. So, there is no reason that there should be a mean of this noise, right. So, I am also going to assume that this noise is uncorrelated in time. Okay. So, in the continuum, that means that eta t prime is delta t minus t prime. So, what is means that if I think of it this time in terms of some discrete steps of delta t. Okay. So, if I can you see up to here? You can see up to here. Just let me know when here. Okay. So, I am assuming that okay. Suppose I just look at that. Okay, I just measure in terms of delta t. So, this delta function means that this noise, if I draw the noise from two different intervals, okay, so that average will be 0. So, in this case, it means that basically eta t prime, this is 0 if t not equal to t prime, and if it is in the same interval, okay, so eta of t, so that is just eta square t because t equal to t prime, this is equal to 1 over delta t. Okay. Okay. The square, the variance of the noise is 1 over delta t, and in the limit delta t going to 0, so what you have is this delta function. Okay. So, now, so given this, so you immediately notice that, okay, so what is the mean? So, mean of V of t is whatever is velocity, okay. So v of 0, so it can be the mean of v of 0 if it is a initial velocity is random, okay, exponential of minus gamma by mt, right, because the this term the mean is 0, so therefore this term does not contribute, okay. So therefore the velocity loses memory, so this mean goes to 0 for t much greater than m by gamma, right. So basically t going to infinity. So infinity in some sense means that t is when much greater than this time scale, okay. So n by gamma is some time scale, I call it tau gamma. So or just let's call it tau. So when t is much larger than this tau, this velocity goes to 0, okay. So now what about the variance? Okay. So I can in fact look at the v square average, okay. So v square average is again v0 square average e to the power minus 2 gamma by mt plus this guy, right. So this guy is coming 2d by m square. So there are, so this integral product of this, so there will be two integrals, right. So 0 to t dt1, 0 to t dt2, okay. Then there are two of these terms, so exponential of minus gamma by m t minus t1 exponential of minus gamma by m t minus t2, then eta of t1 eta of t2, okay. But this one we know, okay, this one we have said that these are uncorrelated in time, okay. So these are delta correlated, so this becomes delta of t minus t prime, right. So therefore you can, okay, this one remains, so you can carry out this integral. So this delta function gets rid of one of the integrals, right. So then you have 0 to t dt1, okay, exponential of minus gamma by m t minus t1 exponential of minus gamma by m t minus t1. So there are two of them, so this two of them, right. Okay. So this integral you can do, yes.
What is capital D?
Capital A. Capital A. Okay. Capital A. Okay. So this one, this. So this integral you can do. So what is this integral? It's just an exponential integral. You can in fact make a change of variable t minus t1 to t prime. So this is same as 0 to t sum dt prime minus 2 gamma by m t prime. So therefore this is m by 2 gamma 1 minus exponential of minus 2 gamma by t. Okay. So therefore we have this result v0 square exponential of minus 2 gamma by mt plus this guy. So what is this? 2 cancels with this 2. Okay. So this is A. M cancels with this. So m gamma 1 minus exponential of minus 2 gamma by mt. Okay. So what happened? So therefore v square t goes to infinity. So what happens to this one? So this is just, this guy goes to 0, this guy goes to 0. So this is A by m gamma. Okay. Now, what do you expect it to be? Right, this is a particle in this bath of this thing. This bath is at some temperature T, right. So, at large time you expect this particle to equilibrate, right, this velocity to be equilibrated, and then when it equilibrates you expect it to satisfy equipartition. So, which says that half m v square, so this is at T equal to infinity, is half kBt, right. So, therefore, you expect this guy A by m gamma is equal to kBt by m, right. So, it says therefore that A is m cancels gamma kBt. Okay. Okay. So, now we know what is this A, okay, and we can just put this A, and this A is independent of whether you have an external force or not, right. Although we have put this external force does not change the properties of this medium, right, this, okay. So, therefore, I am going to come back and write down this equation. So, write down this equation as square root of 2 gamma kBt. Okay. So, I will just substitute A there. Okay. So, this defines my Brownian motion. Okay. So, let me divide this equation by gamma. Okay. So, I write down this m by gamma. So, m by gamma I have defined as a time scale. Okay. So, let me just write this time scale here. So, tau dv dt is equal to 1 by gamma f of x minus v plus. So, this one now if I divide by gamma, so that becomes 2 kBt by gamma, and this one I am going to define another parameter. So, where it says tau is m by gamma and d is kBt by gamma. Okay. So, now I want you to, so this is I think so you will have tutorials in the afternoon, and okay, some of the students and postdocs are taking, and I have also sent some problems, but I am also going to give you some problems here. Okay. So, one of the thing I want you to do, so solve this equation now with this one. So, I have already, okay, so it's there. So, A is basically kBt by gamma. So, you have, where is that? Okay, so the solution was there, V of t was there somewhere. Okay. So, V of t, from V of t find out x of t. So, what is x of t? X of t is 0 to t Vt prime dt prime. Okay. So, given V of t, find x of t, okay. Then find what is average x of t. Okay. So, this is for the tutorial, just calculate this. Also calculate x of t minus x of 0 whole square average. Okay. Which one? D is this one, I have divided by gamma. right? So this square, they say 1 by gamma, this gamma is gone, and then there is a divided by gamma, so that gamma, when I take it to inside the square root, it will be this, right? So find this one. Okay. So what you will see is that for t much less than tau, this should be, so okay, so this should go like this, should be proportional to t square, okay, and for t much greater than tau, you should see that this should proportional to t. Okay. So that's a homework for you. Okay. So now, as you saw here, that when this time is much greater than this tau, right, it forgets its velocity in some sense, right? It doesn't remember what is this initial velocity is, right? It equilibrates, okay? So imagine that you are looking at this particle under this microscope, and you are looking at this particle at a resolution which is larger than tau, okay? So in fact, another question I want you to do is estimate tau. Okay, for a, imagine that this size of this particle is about a micron, right? It's a polystyrene bead, let's say, so it's basically has a similar density as water. So just assume that it has the same density as water. Okay, find out what is tau. Okay, so you'll see that tau, okay, depending on whatever the values you put, it's between 10 to 100 nanosecond. Okay, so now if you are let's say doing a measurement, let's say at microsecond scale or something, okay, so by that time this inertial effect already dies down. Okay, so in that time scale, so you can forget this first term. Okay, so this is the equation you had general, but now if you are doing a measurement, let's say at a time scale which is larger than tau, you can forget this term. Okay, so that approximation is called the overdamped this thing. So okay. So overdamped in which I am going to get rid of this first term. Okay. So because tau I am going to take the limit tau going to 0 in some sense. Okay. So tau going to 0 limit in the sense that I am doing a measurement which is, so my dt time resolution. Okay. Like suppose I am just looking at the particle every microsecond or something, right? So then this term doesn't contribute. So I left with this equation, this one, right? So left hand side is 0. So now if I put v equal to dx dt, okay? So if I put v equal to dx dt, I can take this side on the left. So I have an equation which is dx dt is equal to f of x by gamma plus square root of 2d eta t, right? And where d is given by this, and eta has the property that average eta is 0 and eta t prime is delta of t minus t prime. Yeah. Okay. So this is the equation. Okay. So let's analyze this equation first. Okay. So again, first let's look at f of x is 0. So it's a free particle. Okay. So there is no force. Okay. So then I have a equation which is dx dt is equal to square root of 2d eta of t. Okay. So xt minus x0, so which is square root of 2d eta 0 to t eta t prime dt prime. Yes. So this average is over different ensemble of noise. Okay. Okay. So let's just come back to this. So let's come back to this equation. Let's come back to this equation. Let's say, right? So what is this? So random variable is eta. Okay. So eta is driving x. So if I plot these trajectories, okay, as a function of t x, so what you will see is that, okay, I start from some point. Okay. So imagine that, okay, just look at this equation in some discrete time, and I am just measuring at some time state of delta t. Right. This is a random variable. Okay. So therefore the slope is random. So this guy will go somewhere there. Right. Then the next time it will be go somewhere there. So you will have a motion something like that. The slopes are random. Okay. Now when you take delta t going to 0, so you will have something which will probably look something like a very jagged thing, right? Okay. So the slopes are random. So therefore the random variable is eta. Okay. And eta is driving the motion. So this average is, so what is this average means? So if I want to find out this particle, okay, so if I look at one realization starting from this, so this guy will look something like that. Okay. Then I take another instance. Okay. Cannot see any. Okay, maybe. Okay. So this guy will look the next trajectory again starting from there. It will be. So if I start from the same position, measure at some fixed time t, these positions will be different each time, right? This average is with respect to this noise, okay, and this is coming because of all this, in some sense these particles are hitting this, the water molecules are hitting this particle. So that we are going to come later. Okay. So at this point we are still at this trajectory level. Okay. So now this object on the left hand side, okay, is a random quantity, right? It's a random variable because this is for one realization of eta. So if I start from here and this is my x0 and this is my x, okay. So this is my xt minus x0 for that particular trajectory. Okay. So if I take another trajectory, okay, so this is starting from here and I reach somewhere there, right? So this guy will be my this xt minus x0. So this will vary from one realization to another realization, right? Or if you have lot of particle, you start from the same position, right? From particle to particle, this position will be different. Okay. So I want to find out what is the average of this quantity, right? Sometimes this displacement is starting from here. Okay. So imagine that this is my 0, x0. I can just call it to be my origin. Okay. Sometimes it's here, sometimes it's here, sometimes another trajectory. If I look at it, okay, sometimes it ends up here. Okay. So it ends up in different places. So what is the average? So the average of this quantity, so if I look at x of t minus x of 0, this average is, so average over these noises, right? But I said that these noises are symmetric, therefore this is 0. So, therefore, this average is 0, right. So, on the average this displacement is 0, right. But this average, although the average is 0, it does not tell much about the spread, right, because you can have a particle going somewhere there and somewhere there. If it is symmetrically distributed, the average can be still 0, right. So, it does not say how much the particle typically move. Yes. Yes. So, now therefore, we need to look at the square of this object, right. Square of this object is a positive quantity. So, we need to look at the square of this object. So, that is called the mean square displacement. Okay. This mean of the square of the displacement. So, this is x t minus x 0 whole square this. So, this is 2 d times 0 to t dt 1 0 to t dt 2 eta of t 1 eta of t 2. But this one, this noise is a delta correlated noise, right. So, this is equal to delta of t 1 minus t 2, that gets rid of one of the integral, and then other integral is just the free integral. So, it says this is equal to 2 d times t. So, the variance grows like t. Okay. So, as opposed to a particle which is suppose just moving at a straight line, either positive or negative. Okay. So, mean will still be 0. Suppose randomly you pick up a particle, sometimes it goes left and sometimes it goes right, but some constant velocity. Okay. The variance will be t square, right. So, but here that goes slower than that. Okay. So, the variance goes like t. Okay. So, this is what you should in fact see. So, what you should see is that you should see 2d t. Okay. When you do the calculation from this underdamped equation what I had written before, so what you should see is that the variance goes like t. Okay. So now, so this is a description in terms of the trajectories, right, and from the trajectory description, okay, we have said okay mean is 0 and then okay we calculate the second moment. Okay, we can keep on doing these higher order moments, but instead of doing that we can actually calculate the probability distribution, right. We can say that okay I look at this trajectory, okay, at each time it reaches some point. Okay. So, I note this point at a fixed time t, okay, and I look at where the particle is and I just mark that position and draw a histogram. Okay. So, that gives me a probability distribution, okay, and I want to compute that probability distribution starting from this equation. Okay. So, before doing that, so let me just where is this guy? Let me just start here. So, this equations which basically gives the description at the trajectory level, these are called Landsberg equations. Okay. So, this is the overdamped Landsberg equation because we have ignored the inertial term, okay, and this equation is the underdamped Landsberg equation basically. Okay. So, now we want to give a probability description, and that okay is called the Fokker-Planck equation. Okay. So these processes, so see that this is a first order equation, right, like this dv dt dx dt is a first order. So if I want to iterate this in time, it's a discrete time this thing, since it's the first order, I just need only one instant, right? So if you tell me position at this point, I can tell you the position at this next point, right? So it does not have any memory of the future, of the past, right? So this kind of processes which does not have any memory, these are called Markov processes, okay? So okay, so basically at a given instant, describe the next instant. Okay, so now if imagine that you have a process. So in this case, I have only one random variable. Okay, but in general, I can think of a process where I have n random variable x1, x2, xn, and this guy describe me a Markov process. Okay. So it means that if I look at the space of this x1, x2, xn, so that will be one single point, okay, and that point determines the future, point at the next instant. Okay. So now you want to find out what is the probability, okay, of this process at some time t plus delta t, starting from time t equal to 0. Okay. So this one, since it's a Markov process, so this x represents all the x's here, right? Since it's a Markov process, it should only depend on the probability at time t, because I am looking at the time step of delta t. So I am thinking that, okay, I am thinking something like, so let's say this x I am representing by just a single line, okay, just a point, and this is my time. This is my time. Imagine that, okay, this is something like this x, okay, okay, and this is my t plus delta t, and this is t. So this is my x, right? So that should only depend on the previous step. Okay. So this depends on x minus delta x. Okay. So these are vectors, okay, at time t. Okay. But then it has to go from here to here, right? And this probability of that jump, okay, so can depend on from where it is going, okay, and of course it's a function of delta x. It's a probability. So maybe I should just write it the other way, or okay. So it is a probability of having a jump delta x, okay. Maybe I should just write it like this. So this is a probability of having a jump of delta x, okay, starting from x minus delta x, okay, and then I am integrating over all possible values of delta x. Okay, these are all vectors, right? So this, that it only depends on the previous point and actually not where it is going or not any intermediate point. Okay, this is one of the prescription of basically describing this stochastic calculus, and this prescription is called Ito prescription, basically, right? So it basically depends on the point from where you are starting. Okay, it doesn't matter where you are going. Okay, so now, so this is equal to this, and now you look at this guy. So this is, of course, okay, it's a function of delta x, right? But this guy, there is a variable x minus delta x. Okay, so this I can think of it some function of x minus delta x. Of course, delta x is, this delta x is there. Okay, but I just look at it as a function of x minus delta x. Okay. And now I expand in Taylor series, right. So, what do you get? So, if you expand, so you get f of x, okay, minus, so I equal to 1 to n delta xi del f del xi, right, plus I equal to 1 to n j equal to 1 to n delta half delta xi delta xj del 2f delta xi delta xj, right, and so on.
And will be a function of t also. Because
So, this guy I am assuming that this is not a, yeah, this t is there. So, these things are, all things are there. So, I am just, for the time being I am just looking it as a function of x minus delta x. So, all this delta x t everything is there basically, right. So, this I am just looking at a parameter, I am just treating it as a function of this guy. Okay. So, these other variables are still there, right, okay, and then so on, right. So, then you see that this object, so what is the first term? So, okay, so let us just look at the first term. First term is f of x. So, this is phi of delta x, right, because I am expanding with respect to this variable, right. So, this guy is phi of delta x. So, let me just write down plus infinity. So, d of delta x. So, that one let me just put it before, phi of delta x p of x t. So, this is the first term, right. The second term is minus I equal to 1 to n. Let me just write down minus infinity to plus infinity d of delta x, then delta xi, del xi of phi of delta x, phi of delta x when x p of x t, right. This f is just phi times p, right. Similarly, I write down the half I equal to 1 to n, j equal to 1 to n del. So, let us just do the integral, okay, integral over, so minus infinity to plus infinity d of delta x d of delta x, then what I have is delta xi, delta xj, del 2, del xi, del xj, phi delta x, x e x t, and so on, right. So, that this integral, say this integral is over delta x, this p is independent of delta x. So, I can take it out of the integral sign. So, what is this object? D of d delta x, phi of delta x. The phi of delta x is the probability density of having jump of delta x, right. So, if I integrate over this quantity, that is 1, right. So, therefore, the first term gives me, so let me just write down again. So, p of x t plus delta t. So, first term give me p of x t, right. What about the second term? Second term is this one. In the second term, see there is a derivative, okay, so this I can 1 to n. So, there is a derivative with respect to xi and there is an integral with respect to delta x, right. So, integral I cannot do immediately because see delta x is here, here and here, right. But p I cannot take out of this derivative, but on the other hand this derivative I can take out of this integral, right, because xi and delta x these are independent variables, right. So, therefore, I can take out this derivative outside. So, what I have is del xi, okay. Then what is there inside the derivative? So, this thing I take it out, d of delta x, delta xi, phi of delta xi. So, what is this object? That is the average of delta x. So, that is just the average of delta xi. Okay. It need not be 0. Okay. Times this p is still there, right, times p of xt. So, this del xi x on both, right. So, this guy x on both, right. The third term similarly. So, what is the third term? Okay. So, I equal to 1 to n, j equal to 1 to n. Okay. So, I can take out these guys outside. Okay. D of delta x, delta xi, delta xj, phi. Okay. So, delta xi, delta xj, this average. Of course, there is a half. So, let me just put the half also here, and then I have this p here, right. So, p is still there, and I have, so this x on this both. Okay. Similarly, I have this higher order terms. Okay. So, now this one I can take it to this side, and I can divide it by delta t and take the limit delta t going to 0, right. So, if I take that, so what do I get? So, left side, so I am going to take this side and then take delta t going to 0. So, left hand side I have del p del t, this guy I took it to this side. Okay. So, this is equal to minus I equal to 1 to n del xi. So, this guy is limit delta t going to 0 delta xi by delta t times p. Okay. So, this is this times p of xt. Okay. Plus I equal to 1 to n, j equal to 1 to n del square, okay, limit delta t goes to 0 delta xi delta xj average by 2 delta t p of x t. Similarly, you can have all these higher order terms. Okay. So this is the general Fokker-Planck equation. Okay. But you still have to compute these terms, okay, and similarly these higher order terms. Okay. So now we look at this equation for the process what we had, right, for the Brownian motion. Okay. So I'll just leave this equation here. So what we need to compute is all this guys, right. So now the process we had is a single variable process which is just x of t, and okay. So we have a process which was dx dt is f of x by gamma plus square root of 2d eta t, right. So where average eta is 0 and eta t prime is delta t minus t prime. Okay. So now we want to find out. So we want to find out basically p of x t. Okay. So what is this object? So p of x t. So this means that p of x t dx. So this is the probability of finding the particle between x and x plus dx at time t, right. And if I only look at this guy, so I divided by delta x, so that is what this is. This is called the probability density function, right. It is a density, right. So this is the probability and this is the probability density function. Okay. And we want to find out this. Okay. So this is basically, as I was saying, that okay, you look let the particle evolve from a fixed position, and every time you look at where the particle position is at time t, and you plot a histogram of that distribution, and that distribution is basically this one, right. And we want to find out what is that distribution. Okay. So we already have an equation. So for single variable, what is that equation? So I have a equation del p del t is equal to minus, I have the single variable, so del x of delta x average by delta t. These are all in the limit delta t going to 0. So let me just put the okay, limit delta t going to 0, delta x average by delta t plus del 2 del x square limit del times p delta t going to 0, delta x square average by 2 delta t times p of x t, right. So this is the equation, but we need to basically compute this object and this object. Okay. So how are you going to compute? So we know this equation, right. So we need to look at this equation in a small time delta t, between t and t plus delta t, right. So what is that equation? So if I integrate this equation between t and t plus delta t, okay. So what I have is delta x at time t on the left hand side Okay. So, right hand side is my delta t is very small. Okay. So, I am assuming that this force does not change that much during the position. So, this is basically f of x by gamma times delta t, okay, plus this guy. This guy I have to be bit careful, right. Basically, I have to discretize this noise in terms of delta t, and I said that if I want to discretize this noise in delta t, basically the variance should be 1 over delta t, or instead of doing that, you can also write basically t to t plus delta t eta t prime dt prime, right. So, I will just integrate this between t and t plus L t. So, what is the average? So, when I take the average of this quantity, this is just f x by gamma times delta t, and average of this noise is 0, right. So, therefore, average of x delta x is 0, okay. Delta x square average, I am taking a square, this, right, and then taking the average. So, there is a term coming from this square. This square is something times delta t square, okay. There is a term coming from this square, and then there is a cross term, okay. But cross term is, okay, what is the order? So, this guy, okay. So, let us just look at this term first, okay. So, what is this term? So, this term is 2d times 0 to t dt1, 0 to t dt2, eta t1, eta t2. So, this is this term, square of this term, okay. So, this cross product is, of course, you can think of it to be 0, because of eta and x, they are at that point uncorrelated, because this x was the previous x, okay. And then that term is of order delta t square, okay. So, this plus order of delta t square, okay. So, what is this object? So, this we have already calculated, right, because this I take a delta function, one integral goes out, then I have this second integral. These are not from 0 to delta t, these are from t to t plus delta t, t to t plus delta t. So, one integral goes, then there is another integral which is basically t to t plus delta t. So, that is just 2d times delta t, right. So, this guy is just 2d times delta t plus this higher order term, okay. Okay. It is not 0, sorry, why did I write it 0? So, f x by gamma times delta t is not 0, thank you. Yeah. So, at least you are paying attention. Huh? Okay. So, this is not 0. So, we have delta x, we have delta x square, right. And so, you see that this guy, so therefore, this integral is of order delta t, right. So, therefore, you can think of this integral over one of the noises of the order square root of delta t, right. So, this integral, okay, is of order square root of delta t. That is why when you take 2 integral, you get delta t, right. So, when you see a term like that, you should always think of this is of order square root of delta t, right. So, in that sense also you can see that, okay, this is the average was, okay, so the average this guy was 0, but when you take the square, so this guy that was delta t, but this if you take the multiplication, this is delta t and that is square root of delta t, so delta t to the power 3 by 2. So, this is a higher order term, okay. So, we will see that these higher order terms actually do not contribute. So, now given this, we can write down this equation. So, what is the equation? So, we have del p del t, this is equal to mean I have. So, if I divide it by delta t, then I have fx by gamma. So, I have minus del x of fx by gamma p plus this guy is delta x square is 2d delta t. If I divide it by the delta t and take delta t going to 0, this becomes d, and d I can just take it out of the integral, okay, del 2p del x square. And you see that these higher order terms now, so if you take this model, okay, so we are going to assume that all these higher order terms basically scales. So basically each of these integral scales like square root of delta t. Okay. So when you do these higher order terms, okay, so let's say 3 of this term, it will be delta t to the power 3 by 2, right? 4 of this is delta t square. So those terms, when you divide by delta t, so those terms will go to 0. Okay. So therefore, what we have is this equation. Okay. So this is a first order in time and second order in space. Right? So I have a partial differential equation which describes this. Okay. So now, so we are going to look at two cases for this equation.
Why are we not writing average of f of x?
So why are you not writing average of f of x? So average of f of x means what?
If I do the same thing over multiple histories or multiple
Times.
we have a
So f is defined by the space. Okay, f is not a random function. Of course, f is random function through x. Okay, but at a given space, that f is fixed, right? Yes.
And here we are implicitly assuming that it's not dependent on time.
So we are assuming that it's not dependent on time. Okay, so for the time being, we are assuming that this f is not a explicit time dependent function. Okay, it's just some function. Okay, so given this equation, so we are going to do two things. So first, we are going to solve when f of x is 0. Okay, so I think I have half an hour. So let's first solve this thing. So let me just write down this equation here again. So del p del t is minus del x of f of x by gamma p plus d del 2p del x square. Okay. So we are assuming two things. Okay. So we are assuming that f is not a random function, and we are also assuming that this d is not a space dependent function. So we are assuming d to be constant. Okay. So if we have,
So this equation is Fokker-Planck equation for overdamped case.
so this is the Fokker-Planck equation for the overdamped case.
So do we calculate it for normal underdamped also? Or we do
So if we calculate for the underdamped, so maybe I'll just come back to that later. Okay. So now the underdamped equation I have written down. Okay. So that's a Markov process for the velocity, right? Because it's a first order equation in first order differential equation in velocity. But if I write down this equation for the position, okay, so it will be second order differential equation for the position. So not a Markov process for the position. Okay. So what I have to do? So I have to define basically position and velocity separately. So I have to write down an equation which is dx dt is v, and I have another equation m dv dt is some f of x minus gamma v minus, now I know this coefficient now, t times eta, right. So, I have to write down two equations. So, now I have a two variable x and v. So, these are first order in x and v. So, therefore, if I give you x and v, I can tell you the next instant, right. So, this is a Markov process in x and v. So, for that you have to write down a Fokker-Planck equation for x v t. So, it is a two variable this thing. So, you can still use the same one. So, there will be term like del del x, del del v, there will be term like del del 2 del x2, del 2 del v2, del 2 del x del v, and you have to calculate all these moments, and you find it, okay, some of these moments will be 0, okay, but that equation will look very different from this equation. And in fact, going from that equation to this equation is quite non-trivial actually, right. So, maybe let us just write down that equation. So, what is that equation? Maybe let us just write down the Fokker-Planck equation for the underdamped case also, right, because we just need to compute this thing, right. So, this is for overdamped. So, let us just write down for the underdamped. Okay, for P of x v t, right. So, we need to compute what? Average x. So, that we know. So, delta x is v delta t, right. So, delta x by delta t is v, okay, limit delta t goes to 0. Okay. So, this one is easy. Okay. There is no delta x square term, right, because delta x square term will be v delta t, that will be delta t square term, right, and we know that delta t square term will not contribute because that will go to 0, right. So, x only we have this one, okay, this, okay. So, v, so what is delta v? Delta v by delta t, limit delta t goes to 0. So, what is this term? So, this term does not contribute. So, it is going to come from here and here, right, divided by m. So, it is 1 by m f of x minus gamma by m v, right. So, now we want to look at the term coming from square. V is a variable, there is no V average. V is the random variable in this equation. You average the delta V's, right. Delta V's and delta x you average, okay, because that's you are evolving in a very small time. Okay. You are saying given your x and v, you just evolve for small time delta t, and what is the average of delta x and delta v in that time, right. So, these guys, we are looking at this guy, we are just evolving at a short time between t and t plus delta t, right. So, what is delta v square average? You see that again like last time, okay, dv is basically 1 by m dt for this guy. So, that guy will be delta t square. So, only term is going to come from this one, right. So, it is 1 by m 2 gamma kbt, right, and then these two integrals of the noise, right, 0 to t dt1, 0 to t dt2, t2 t plus dt, dt1, t2 t plus dt, dt2, eta t1, eta t2, that average. So, that average we now know, right, we are expert in calculating that average, right. So, what is that average? Delta t. So, this is delta t, Okay, 1 by m square, correct, right? And there are no other terms, right? Because if you multiply with delta x to delta v, you see that delta x is for order delta t, and then this guy is of order delta t, so those will be higher order terms, right? So therefore, these are the only terms we have. So now we can write down the equation. So what is the equation? Del p del t is equal to minus del x. V is independent of x, so I can just take it outside, minus v del p del x. There is no second order term in x. There is now delta v. So delta v has two terms. One is this guy and one is that guy. This guy, of course, can come out of the integral. So what is that? Minus 1 by m fx del p del v. This guy is coming from this one. This guy, of course, cannot, the v cannot come out of the integral. So this guy gives me, let me just write down. Okay. Plus gamma by m del v of vp. So this guy is coming from this one, from these terms, right? And there are no other first order terms. Then there is a second order term, right? So what is the second order term? Second order term is gamma kb t by m square del 2 p del v square, right? Did I put everything correctly? I think we got everything right. Okay. So this is this equation. If you want to write down, so kbt is okay. So what is d? D is kb t by gamma. So you can put it there. So if I just so gamma square. Okay. So this one. So this one, if I want to write down in this thing, so this is d by m by gamma whole square. Okay. Yes. Which one? Yeah, these are independent.
No, in last case, why it wasn't?
This case,
Yeah.
because so this case, because we have a equation which is, what was the equation corresponding to this equation? We have a equation dx dt is equal to f of x by gamma plus square root of 2d eta t. So for this random process, there is no v. This is the overdamped limit of the random process. So there is no v for this one, right? So therefore, random variable is x. On the other hand, this underdamped case, as I say, that only x is not a Markov process, right? Because it's a second order equation in x. So I need to define x and v. The combined thing is a Markov process. Therefore, I need to write down the Fokker-Planck equation for the combined process. Now you see that this is quite different from that equation actually, right? The second order term here in x, that comes in v, right? X only appears as a first order derivative, right? Also with x, all these things doesn't come, right? And so going from, you can ask, okay, so I know that if I take p of x v t, and if I don't care of v, this integral is giving me this p of x t in some sense, right? And that should satisfy an equation of this kind, no? Right? But you know that this satisfies this equation only in certain limits, right? When t is much larger than this time, t by gamma, in the sense, some sense this guy is going to 0, right? So therefore, we cannot just expect that if I just integrate this equation, whatever this guy we have, we just get satisfies this equation, right? And going from here to here is a bit non-trivial actually, okay? So maybe, okay, if we have some time, we can do, but okay, I mean, otherwise I'll just give you some reference for this one, okay? So now we are going to focus on this equation, okay? Yes, so in fact, so given that we have written down this equation, so I'll give you an homework problem, okay? So if your f of x, so again homework, so take f of x to be a force which is u prime x, okay? So then take t going to infinity limit of this equation, this solution, okay? So last time when t goes to infinity, so p of x vt when t goes to infinity, okay, we expect it to be a time independent state, okay, and show that that state is an equilibrium state xv, which is given by minus beta h, okay. So where h is half mv square plus e of x, right? So you show that actually it satisfies the Boltzmann this thing, okay? So you get the Boltzmann distribution. Okay. So t going to infinite limit, you take this side. So you are looking for a time independent solution. So left hand side is 0, and substitute this solution, okay, where f of x is given by this, and verify that this is indeed the solution of this equation. Okay, maybe we can just do it in the tutorial. So I have about 15 minutes. So okay, so do you have any questions? Then otherwise I'll just go to the So what should be the boundary condition for this equation? Yeah, that's a good question, because given a equation, I need to give you initial condition and boundary conditions, okay? So in this case, you can take the free boundary condition. So if you start with any small x, small v, okay, you don't expect at any finite time to go x to infinity. So p of x vt should go to 0 when x goes to 0 infinity or minus infinity, and similarly it should go to 0 when v goes to plus infinity and minus infinity. No, that's the boundary condition, and then solve it and whatever you get, right? So boundary condition is only at the boundary, right? I don't have to, and I need to give an initial condition. You can take any initial condition. You can take delta function initial condition, right? Saying that, okay, I start with a fix x and fix v. So now I'm going to solve this equation, right? So let's just so do all these exercises, because you will need it next week actually. Many of these things you will need it. So just do it this thing. So let's do the case f of x is 0. So what is the equation? So I have equation del p del t is d del 2p del x square. Okay. So this equation, this is a diffusion equation, right? Okay. So in fact you can solve this equation in many different ways, okay. So what we are going to do, we are going to do the simplest way, and we are going to do Fourier transform, okay. So the same Fourier transform, I am just going to just give a fancy name, and which we are going to say characteristic function. Okay. So, characteristic function is nothing but the expectation value of e to the power I k x, right. So, which as you see that when you take the expectation value, this is e to the power I k x p of x, t is okay is hanging around, but for any variable this is just the definition, right, exponential of I k x is right. And this guy, just let us call some p tilde k, which is of course a function of t, because instead of writing this long thing, that is easier to write down this. Okay. And how is p of x related to this guy? Is the inverse Fourier transform, and p of xt is related to this p tilde. So, if I can find p tilde, so that is basically minus infinity to plus infinity. Since I did not put this, say sometimes when you define this Fourier transform, we just put 1 by square root of 2 pi in both places. But here, since I did not put it here, I am just going to put all the thing here. So, it is 2 pi. So, this is dk by 2 pi exponential of now minus I k x p tilde of k t, right. So, I need to find this, and if I find this, I can just do an inverse transform. Okay. So, now let us just multiply e to the power I k x in that equation and then integrate over x. Okay. So, this equation let us just call it equation 1. So, I take integral minus infinity to plus infinity dx e to the power I k x to equation 1. Okay. So, what do I get the left hand side? Left hand side, this integral is over delta x and this differentiation is over delta t, so that I can just exchange, right. So, I can take the integral inside. So, I have is delta p tilde k t delta t. Okay. So, what is the right hand side? Okay. So, right hand side let us just calculate. So, let us just calculate the right hand side here. So, minus infinity to plus infinity dx e to the power I k x del 2 p del x square, right. I mean this d is there, but this is the only thing, right. So, I am going to do by parts, right, because I want to get rid of these derivatives, right. So, when I do parts, so first term is e to the power I k x, I am going to integrate this guy. So, when you integrate this guy, it is del p del x minus infinity to plus infinity, then minus this other guy e to the power I k x del p del x dx. So, this guy I am going to assume that this both derivatives and this function vanishes at x goes to plus minus infinity, right, because if I just start with at any finite point, it cannot basically go to infinity at any finite time. So, this guy goes to 0 at this boundary. This guy I am going to, and this guy if I differentiate, so there is a I k, right. So, there is a minus I k. Okay. So, now I am going to do this one more time. Okay. So, this guy if we do one more time, so this minus, so there is a minus sign. So, there is a again a boundary term is just e to the power I k x minus p minus infinity to plus infinity, and then minus, so this minus I k was already there. There is one more I k and minus infinity to plus infinity e to the power I k x p of xt, right? So this guy again vanishes at the boundary, so this guy goes, okay. So this is just p tilde kt, that was my definition of p tilde. There is a ik here, there is a ik here, okay, minus minus, that minus goes becomes plus, okay. Ik times ik, so minus k square, so therefore this guy is minus d k square p tilde of kt, okay. So this is a equation, you know the solution, right? So what is the solution? P of p tilde of kt is p tilde of k0 exponential of minus d k square t, right? So therefore I just need to do the inverse transform, okay. So what is the inverse transform? So given this, so I need to compute, so maybe let's just do it here. So p of xt is equal to minus infinity to plus infinity dk exponential of minus I kx, and this guy p tilde of k0 exponential of minus d k square t, right? But I need to find out what is p tilde of k0, right? So what is p tilde of k0? This is just putting t equal to 0 here, right? If you put t equal to 0 here, so this is minus infinity to plus infinity dx e to the power I k x p of x0, right? So this is the PDF at the starting position, okay. So let's just give a different notation, we just call it p0, right? So this guy, okay, and x is a dummy variable, right? So we just call some other variable, just call it x0, dx0 e to the power I k x0, and this guy, okay, this x is x0 because that's a dummy variable, and this initial distribution, right, this is a distribution at time t equal to 0, this is something I have to give it to you, and that distribution I will just call it p0, this is a different function, I am just giving you this function, okay. So therefore this is what this guy is, so therefore we can just put it there. So what do we have? So we have an integral over, so this guy we are substituting, right? And these integrals we can exchange over k and x0 because these are independent this thing. So let's just write down minus infinity to plus infinity dx0 p0 of x0. But this guy depends on k, okay, so I have to put inside the k integral. So minus infinity to plus infinity dk by 2 pi exponential of minus I k x minus x0 e to the power minus d k square t. Okay, I have to evaluate this integral. Okay, so this is a Gaussian integral, right? I just need to complete the square, okay, and then evaluate. Okay, so this is, I will leave it again as a homework problem, okay, but what you should remember, maybe I will just write it here. some properties of Gaussian integrals. Okay. So, some properties of Gaussian integral. So, if I give a Gaussian function, let us say g of x, which is, so g sigma of x, suppose I define this function e to the power minus x square by 2 sigma square by square root of 2 pi, okay, sigma square. Okay. So, check that minus infinity to plus infinity z sigma of x dx is equal to 1. Okay. Also check that minus infinity to plus infinity e to the power of minus e to the power of I k x z sigma of x dx is e to the power of minus k square sigma square by 2. These are all you are supposed to check. Okay. And also check that suppose I have a function, Gaussian function with a given mean, right. So let's this guy's so also check that. So these are all you have to check, right. So also check that if I have a some function e to the power I k x z, forget about this sigma, okay, just a, it's not telling you anything, right. Z of x minus mu, right. So it's basically if I put x minus mu will go there. So that's a Gaussian distribution with mean mu and variance sigma square. So dx, now you see that if you just make a change of variable, right, x minus mu you call it something y, right. So what do you get? So x minus mu, if you just call it y, so x is y plus mu. So you will get that e to the power I k mu dy minus infinity to plus infinity e to the power I k y g of y, right. So therefore e to the power I k mu, and this guy, you know, this is k square sigma square by 2. So minus k square sigma square by 2. Okay. So these are something you should check. And so what it says that this characteristic function, so this guy, so maybe let me just write it here. So this characteristic function which p tilde of k, which we are calling e to the power I k x, you can also write it as a exponential of some g of k, okay, and this g of k is called a cumulant generating function, okay, and if the cumulant, and this is called the moment generating function. So if the moment exists, okay, so it says that this function, if the moments exist, so it's possible that some moments do not exist, okay, then you can find p of k, but it will not be Taylor expandable about k equal to 0, right. So if the moments exist, then only you can expand in Taylor series about q equal to 0, and it says that then you can put 0 to infinity I k to the power n by n factorial x to the power n, okay. It generates all the moments. So if you know this p of k, basically if you expand in Taylor series, you get all the moments, right. So therefore this guy is a moment generating function. So similarly this guy is, cumulants are defined by g of k is n equal to 1 to infinity I k to the power n by n factorial x to the power n. So, this C is called the cumulant, okay. And we know that first cumulant is the mean. So, this starts from 1, okay, as opposed to this starts from 0. First cumulant is the mean, second cumulant is the variance, third cumulant is called skewness, and fourth is kurtosis, and so on, right. So, Gaussian is a distribution. You see that now this guy is exponential of something, right. We are expanding in the cumulant, right. So, this guy, these cumulants, only the first cumulant and the second cumulants are non-zero. So, Gaussian distribution is the distribution where only the first and second cumulants are non-zero. I mean, first cumulant can be 0 also, mean can be 0 also, okay. So, it is basically this thing, but all the higher order cumulants are 0, okay. So, given this guy, so you know that this is of this form, right, because this equation is, I have just done, so minus dk by 2 pi e to the power minus I kx, right. And then this inside thing is e to the power I k x0 minus d k square t. So, this guy is like this guy, okay. So, you can read out the mean. Mean is x0. What is the variance? So, k square sigma square by 2. So, k square you forget. So, this is k sigma square is dt. So, sigma square is 2 dt. So, therefore, you can write down the, when you invert this one, that is the inversion of this distribution, right. That is basically g of x mu, right. So, therefore, what is this guy? So, p of xt, so maybe let me just write down somewhere here in big. So, p of xt is minus infinity to plus infinity dx0 exponential of minus not exponential, what is this? P of x0, p0 of x0 exponential of minus x minus x0 whole square. This is g of x minus mu, right. This is what I am writing. This is g of x minus mu. Mu is x0 divided by 2 sigma square. 2 sigma square is 4 dt. So, 4 dt divided by square root of 2 pi sigma square. So, this is 4 pi dt. Okay. So, this is the full solution. Okay. So, you see that if you have a p of p0 of x is suppose a delta function, if you start with some fixed position instead of a distribution, right. So, what is the what do you get? So, if you take the case p0 of x0 is, let us say, delta x0 in some position, let us say x1, right. So, what is p of xt in that case? So, I just have to put this guy and do the integral, and when I do the integral over x0, just x1 becomes x0, right. So, this will be basically exponential of minus x minus x1 whole square by 4 dt divided by 4 pi dt. Okay. So, therefore, this guy, whatever this Gaussian thing, you can think it of it is a propagator, right. So, it is a going from, for a delta function condition, okay, going from x0 to x in time t, okay, and then you average over the initial this thing. Okay, so this guy P of xt in general is minus infinity to plus infinity dx0 P0 of x0 xt x0 0. Okay, so this is the propagator, and this propagator is Gaussian basically, right? I think I'll just stop here, and then tomorrow we'll do something else. Yeah. And if you have any question, you can ask me or also at the tutorial. Yeah. Yeah. Okay. Any questions? Okay. Okay. So then we'll have tea, I guess, right? We'll have tea, and then we come back here at 10:30, 11:30.